Okay, so recording is started. Get you back to the screen with practice quiz problem just number 1. So I'm having a computer issue here. My normal desktop had given out on me, but since I fixed it, but I'm still, it was just recent that I got it fixed, and so I still have everything set up on my backup computer, but everything is working a little bit awkward and different here on this backup computer. Alright, anybody still need more time on problem number 1? Alright, let's go ahead and look at it. So, I'm going to use, so my Wacom tablet isn't working properly with this new computer. So I'm going to draw a really crude sketch with this with my mouse. Okay, so when this is 7, the input is 7, the output is 19. So I know the function goes through this point. But how does it go through this point? Well, we're given information about the slope. It runs through this point almost horizontal. If it was a negative slope, it'd be going downhill. Positive slope uphill. This one is barely positive. It's almost 0. So it's going through this point right here, but in such a way that it's barely going uphill. And I exaggerated the uphillness of it. It really should look pretty flat. Okay, now if we're going to estimate f of 8, imagine that we knew this function all the way up until 7. It's kind of like projecting into the future. Maybe 7 is an input that represents the current year or something, current time. And our best estimate for what f is going to be a year from now, f of 8, is going to be what it is right now. But we should adjust slightly for what we know is the slope of the line coming through it. Since the slope is positive, it should be a little bit bigger next year. If the slope was negative, it would be a little bit smaller next year. Now, the slope represents the change in the output, the change in f, every time the input increases by 1. So when f increases by 1 from 7 to 8, if the derivative was 1, then it would also increase by 1. If the derivative was 2, then every time f increased by 1, the output would increase by 2. But the derivative is 0.02. So plus, since the input is increasing by 1, the output is going to increase by, not by 1, but only 0.02. Every time the input increases by 1, the output increases by 0.02, provided we stay on the tangent line, which is equal to equal to 19.02. Filled in for me. And so that's what we'll get. Now, this might be a new way of looking at the derivative, a new way of putting things together for you. Or it might have been really intuitive and you might have gotten this ahead of me. Tell me where you're at. Give me a little feedback. This is an important type of problem for us. If you couldn't get it before me, but it's totally understandable now, that's good feedback. Anything that you have. Yeah, it's a different way. It's the same thing, the derivative, but a slightly different way of looking at it that allows you to project. All right, now let's go to number 2. G of 13 is 120. G prime of 13 is negative 3. Estimate G of 15. All right, I don't want to rush anybody. Anybody feels like they might get it but need a little more time, let me know. Otherwise, I'm going to start with this. All right, so if the input is 13, the output is 120. How is the function running through this point right here? Well, we know it's going in a slightly downward fashion because it's negative. And every time this moves 1 to the right, this one falls 3 units. So we're going to here G of 15 is going to equal G of 13, so which is 120. So our best estimate as we guess into the future, this time maybe 2 years into the future, is that's the price that it was 2 years ago. And then we adjust for Now, if we went 1 unit to the right, we'd go down 3. We're going 2 units to the right, so we should go down 6. Equals 114. Alright, so let me know with feedback here. Did you need to see it a second time to be able to get it, or could you get it this time? And maybe do you need to practice this a bit more, or you figure you got it now? So a little bit of feedback. Okay. Right. Why the 6? Let me go over that again. Alright. So the slope is the change in the output every time the input increases by 1. That's what it means to be the slope. So if the input changed from 13 to 14, G would change from 13 down to negative 10. And then we went from 14 to 15, we did it again. The input changes plus 1, and we go down 3 one more time. So going down 3 twice gives us the minus 6. Alright, let's go to the next one. The height of an object is given by that equation. Describe the motion of the object. Include its starting height, initial velocity, acceleration, and draw a picture of its flight path. Alright, anybody need more time? Let's look at it this way. If I have this h of t, all it is 700, then the object is sitting at a height of 700 feet for all time, stationary, never moving. If I include this part into the equation, then the object at time 0 was 700 feet high, but at time 1 it was 702 feet, time 2, 704 feet. So it's moving upward 2 feet per second. So 700 is the initial height. 2 feet per second upward velocity was the initial velocity. That'll also show when we do the equations of this. And then this, if we include all of this, that first part includes the acceleration due to gravity. And if we take the derivatives now, insert now. So h prime of t, when you take the derivative, that becomes the velocity. And that gives you negative 9.8 t plus 2. And notice, so that's the velocity. Initial velocity, we usually just say v when t is 0. If you stick 0 in for the t in this equation, you'll get 2. It tells you the initial velocity was indeed 2. And the initial height, h0 was 700. That's the initial height. And when you take h double prime, that's your acceleration. And taking the derivative of this is negative 9.8. The 2 drops off. And the acceleration stays constant. That's the initial acceleration, the final acceleration, all the way. Constant acceleration. And negative 9.8 must have been meters per second, because that's the units on the surface of the Earth of acceleration. All right. Then, if we describe the motion, the flight path of the object, I could draw a picture like this, where this is time, this is height, and this is going to be a downward parabola starting at 700, but we go up first, and then we're going to reach a peak, and then we're going to go down. So wherever it was 700. And it's part of a downward parabola. Now, does everybody agree that this is the flight path of the object? Or is there anybody who disagrees? Take a minute to think about that. Is that the actual path that the object took while it was traveling? All right, let me send you to your group for a moment. Discuss that, and I'm going to pick on a group in a minute. Is this the actual flight path of the object? pick on group 4. What do you say?
We've said that no, it's not the actual path, but we haven't talked. We haven't like said why.
You haven't said why. Okay.
Yeah.
All right. But your instinct is that no, it's not the actual flight path.
Yeah, because you keep asking, are we sure?
Because I keep asking it, it couldn't be yes. All right. So let me open it up to anybody. If this is not the actual flight path, what is the actual flight path?
This is just a function, a position function with respect to time.
Mm-hmm.
But
If it started here and if we drew it on this axis, what would it look like?
on which axis? I'm sorry.
With a T axis and an H, on the same grid, what would it look like?
If it's starting at 700 feet,
Yep.
It would start, I think, at the 700 feet, but I don't know. I'm sorry, I'm not understanding your question exactly. Because if it's starting at
it starts at 700 right here, actual flight path. Let me give anybody else a chance to make a wild guess. Actual flight path.
So since it's a downward parabola, wouldn't it go underneath the 700 height?
Eventually it's going to. But
But
it
I mean
was
the
thrown up
vertex.
initially with a 2 meters per second initial velocity. So it does go up for a little while. Okay, it's kind of a tricky question.
is it going up, like linearly, kind of like going, like ascending at an angle, like going up but then coming down, or
like a straight line? That's a good guess, but not quite. It's, if we look at this, the height including it draw its flight path, there's no indication in here that it was given any sideways velocity. And so, I mean, it's not totally clear on this, but it looks like it was thrown straight up from what it's saying. And so its real flight path is just here and then here. Punk, and then it comes down to the ground. But we extend that to make it look like this when we artificially put this time axis out here. It's not really the path of the flight of the object. It's how we imagine it when we put a time axis on it. And when you look at this picture as this red curve that just goes up and then comes right back down on itself, you have no idea about that it was moving very slowly at the beginning. It came to a stop up here, and then it was going faster and faster and faster and faster on its way down. But we do get that when we extend it out in time, because the slope is the speed at which it's moving up. It's moving up at a slow slope, and it's slowing down, and then it stops here because the tangent line is horizontal. And then the tangent line is steeper and steeper as you move down the parabola. And so it's picking up more and more speed as it comes across here. So that's why we prefer to, even though it's not the real flight path, we prefer to extend this out with time. And even though the object probably just went straight up and straight down, we get a better idea of how it went up and down when we put this t-axis here. All right, give me a little feedback on this. Was the review important here, or did you already have it, didn't really need the review? Could you use more review on this? Did it add insight? Did it cause you more confusion? Whatever. Alright, let's come to number 4. We lost the number 4 here, so put that on there. Alright, so ignore to the left of the y-axis. To the right of the y-axis is what we're in. An area underneath this shaded might be important. So if x is the hours traveled and y is your speed in miles per hour, estimate the distance traveled between 0 and 3 hours. So this one is a little advanced, and it leads us into a new section. So I'm going to have you work on your own for a little while, and then work in your groups. Compare ideas in your group, and I'll call on a group in a little while. Okay, anybody need more time? Let me go to group 6. Any ideas here?
I think we're gonna have to pass on this one. We still have no idea.
No idea. Okay. Let's go to group 2. Any ideas here?
We had like some low and high estimates, kind of like in the mid 20s maybe, just looking at the graph, like trying to break it up into geometric shapes.
So in the mid what you said?
Like in the mid 20s, like
In the mid
maybe
20s. Maybe 20 miles or so?
yeah, just breaking it up into like geometric shapes.
Okay. And when you were breaking it up in geometric shapes, why were you breaking it up into those shapes?
Because I'm looking at it like if the graph, like you've shaded it in there, so like if you're traveling X, the miles that you've covered is all the region shaded in blue. So we're trying to like figure out how much.
You're saying then that the miles traveled is the same as the area?
Yeah, I think so.
Okay, that's and maybe the problem
Like over.
itself was giving you that hint since it shaded that.
Yeah.
let me ask group 3. Does it make sense to anybody in group 3?
I thought it was a exponential function, so it has to be x to the y.
Okay, it could be kind of like an exponential function. And then the type of function, we could try to get some hint from that. But does it make sense that the area under this would be the distance traveled? Or does that not make sense?
I could see that, but I think you're accounting for the extra space in the volume instead of just the slope itself.
Ah, okay. So let's take a look at this. And let me say, if I was going to draw a constant height for this that had exactly the same area as this, where would I put that constant height? Would I put it up at about 20? No, that's way too high. Would I put it down at 5? Well, the area that I would get in this region has to make up for all of this area over here, so that'd be too low. Maybe about 10. Then the area up here would fill in there, maybe a little bit below 10. I'm going to say right around here. To me, visually, trying to go straight across, but I'm using my mouse today since my Wacom tablet isn't working with my backup computer. All right, I'm saying that this red area is about the same as that other shaded area right there. Now, suppose I had put that at 9 miles per hour. Now, if you traveled 9 miles per hour for 3 hours, clearly you travel 27 miles. And you would take 9 times 3, and you'd get the area. It makes sense that the area under the curve is the distance traveled if this is a constant traveling speed. And what you're doing, in fact, whenever you're multiplying 9 miles per hour times 3 hours equals, notice how the units will interact. The hours cancel each other out. You get 27 miles. Anytime you're doing any multiplication problem, you can always view it as an area problem. Put one on the x-axis, the other number on the y-axis, and the multiplication is just the area of that rectangle. And it also is true that the area underneath this original picture, if it matched exactly with the area underneath 9, that would be the distance traveled. So the distance traveled, let's put it over here. Distance traveled is the same as the area under the curve. And we can estimate areas under curves by trying to estimate an average height. It went from, a height of about 2 up to a height of about 28 maybe, but just visually it looked like, well, it's about the same area as if I had at about 9. So, and we'll say that it's approximately 27 miles. All right. Well, I didn't expect that you would get this one, but I want to know if it's clear or if it's kind of confusing. Do you need more explanation, or are you good with this? Because I'll refer to this later on in today's lecture, and I just want to know if that was good and clear. All right. Not too clear if the shape was different. It would be really a rough, it could be a very hard estimation to, what's an average height. And you might have to draw that horizontal line in a few different places and erase until you feel like, oh, the area underneath the horizontal line is about the same as the area underneath the curved line. Oh, we're going to ignore when it goes beneath the x-axis. That's a complication that we'll eventually get to. But right now, that's a good point. We're just going to do areas above the x-axis. All right. And that's it for the practice quiz. And questions on homework. And let me see if my tool for... Actually, I'm going to do the homework question on the whiteboard. Let me set that up. So there was 4.4, I believe that was, you had to have in for today. Number 29. And Gerardo, that's on 4.4, I'm assuming. And 7. All right. So let's go to the camera. All right, these are 4.4, number 7. All right, we want to sketch a graph with these properties. Alright, so what we notice is to the left of 3 and to the right of 3, we're going to have different shapes. But we have a function whose derivative is negative the whole time. So it is decreasing the whole time. But it's decreasing in a way that the second derivative is negative. So it's decreasing the whole time, but it's concave down on this left half. And it's concave up this right half. So I've got to be decreasing in such a way that my bowl does not hold water. Here's the inflection point. Now I'm going to be decreasing in such a way. Still decreasing, but now this bowl, if it kept this pattern, it would hold water if it went on up. So that's number 7. Let me insert that in. And then number 29. Any questions on number 7 before I erase it? Are you good with that? Make a complete graph of f of x is 3x over x squared minus 1 Alright, so I'm going to make a master table. I always put 0 in. It's an easy point. And I'm going to get 0 out. And that point is my opposite letter y-intercept and my x-intercept. Okay. And then as far as intercepts go, that's the only thing we need to have. Try to set the x equals 0, then try to set the y to 0. But this already has the y being 0. So it's got all intercepts here. And then we're going to take and try to find our critical points. So I'm going to take f prime of x, and I'm going to do the quotient rule. So it's bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared, which is negative 3x squared minus 3 over x squared minus 1 squared. And then I might simplify that further. F prime of x equals, if I factor out a negative 3, I'm going to get x squared plus 1 over x squared minus 1 squared. If it hadn't have turned out to be the wrong sign here, if that had been a minus 1, then we could have reduced. But when it's a plus 1 and these don't match exactly, we can't simplify that anymore. Okay, so then we set f prime equal to 0. Alright, when you have one fraction equal to 0, either the numerator is 0 of this fraction, in which case you get a stationary point. Or the denominator equals 0, which gives you what's called a singular point, somewhere where the derivative does not exist. Now, x squared plus 1 can never, well, negative 3 is stuck at negative 3. X squared plus 1, the smallest it can ever get is 1. It can never be 0 because x squared is always positive. At smallest, it's 0. All right, so there are no stationary points. There's no points that have the derivative 0 in its classical way. But if you set the denominator equal to 0, take the square root of both sides, and then factor this, you get x equals negative 1, x equals positive 1. These are critical points. All right, but these do not exist. Because they cause the denominator to be 0 even in the original function. And that's typically the case. If it causes the denominator to be 0 in the derivative, it usually causes the denominator to be 0 in the original function as well. The original function does not exist there. It's not a critical point in a sense that it has a horizontal tangent line. It's a critical point in the sense that we're going to possibly change from increasing to decreasing as we cross over these vertical asymptotes. These are actually vertical asymptotes of this. Now we have to set f prime prime. Now this was our smallest, our most compact form of f prime. So f prime prime of x would be bottom times the derivative of the top, and the top you can just think of as this if you distributed that out, and that's derivative is negative 6x minus the top times the derivative of the bottom. When I take the derivative of the bottom, I get a 2 to the first, and then chain rule, derivative of 2x. All over the bottom squared. Okay, so f prime of x. Now, notice the numerator has 2 terms. Alright, hold on a second. Negative, yeah. Alright. I think I'm going to have to square this thing out, multiply this out.
Wouldn't the denominator be squared again?
Oh, the denominator was originally squared, so squared again, it's to the 4th power. Thank you very much. All right, the numerator has this and this in common, and it also has a negative 6 in common. So I'm going to factor out negative 6 x squared minus 1. And what's going to be left over from the first term in the numerator is x. What's going to be left over in the second term, this negative 3 times 2 is factored out. I'm going to have a minus 2x, and then x squared plus 1. Okay, and then this is going to be minus 2x cubed when you FOIL this, minus 2x, so it's going to be x minus all that. Alright, and what's going to also happen is this is going to reduce this down to a 3. Negative 6. This x and that minus 2x makes minus x minus 2x cubed all over x squared minus 1 to the third, since that reduced. Alright, now we're going to set f prime prime to be 0. And there's two ways to set f prime prime to be 0. The numerator could be 0 or the denominator. Same two choices that we had before. When you set the denominator to be 0, you'll get exactly the same two answers. These are critical points and inflection points. When you set the numerator equal to 0, the negative 6 we'll ignore. You can't set that to 0. You divide both sides by negative 6. And you'd get 0 equals negative x minus 2x cubed. And then factor out a negative x. 1 minus 2x squared. And then,
Wouldn't that be plus?
thank you. And then this can never be 0 because x squared is always positive, and then you're adding 1. So the only thing this one is x equals 0 is an inflection point. So this is also an inflection point. Okay. And the only has 3 things in our master table, and 2 of them do not exist because they're vertical asymptotes. Now the camera is flashing. I'm seeing it, tons of flashing. It's not working too good with my backup computer here. Sorry about that. I'll get back to the regular computer tomorrow. All right, so then we would put all this information in. I'd probably want to put in a couple other points just to have a few points on this table, like something 0.5, negative 0.5, something to the right of that, maybe 1.3, negative 1.3. A few things that I would plug in, and I'd make my vertical asymptotes, and then I'd have to make my regions of concavity, and also regions of increasing and decreasing, and then put this all together to make a complete graph. Alright, so I'm not going to have time to go through all of that. So I want to make sure that we can get through everything in the section today for 4.9. But that's how we can get going on that one. Let me, oops. this into here. All right, we will take a break right now, and we will start again. At 12:43 p.m. See you in a little bit. Give our love to Adrian. Okay, we're going to start up again. We're going to go to 4.9, Antiderivatives. And the topic of derivatives is the central topic in calculus. And there's a second essential topic in calculus, which has to do with the reverse of the derivative, which we're going to start out calling it the antiderivative. Later we'll be calling it the integral. But the idea of it is it's the inverse function of the derivative. Okay. And so how we're going to start our inquiry into this is with some questions. So if we know f prime, but wish to know f, this is the reverse of the direction that we've always gone before. We've known the function, and then we've said, all right, what's its derivative? But what if we know the derivative, but then we wish to know the original function? Then we would need something, not a derivative, but an antiderivative that would bring us back to the original function. So the problem that leads into this is a pool. A pool is draining at the rate of 15 gallons per minute. T is the number of minutes the pool's been draining. Y is the gallons of water in the pool. Number one, translate the pool is draining at the rate of 15 gallons per minute into mathematical symbols, and try to use the function like maybe an f and these variables, or you could do any of these with f or y's or t's. So I want you to do that. Just do it independently at first, and then enter your answer with your groups, and I'll call on a group in a minute here. Okay, anybody need more time? Before I call on a group, I'm going to suggest an answer. Y of t is equal to 15. And I'm going to call on group 6. Is that answer, do you agree with that answer or disagree?
Would say I would agree with that.
You agree with that?
It's-
It seems
it's-
pretty reasonable. Y of t is equal to 15. But let's look at this more in detail. Y of t equals 15 means that after any time t, after any time t, because the input is the time, there are 15 gallons of water in the pool. So this actually means it's not draining at all. If we went to y of t equals 15, it means there's always 15 gallons of water in the pool and it's never draining. So we're going to need to adjust it. Instead of that being the answer, let me go to group 3. Any ideas? For translating a statement into mathematical symbols.
We just got y of t equals 15x, or you could put f of t, whatever.
Ah, so y of t, let's keep it, capitalize it. Y of t is equal to 15, and put the input variable. Let's put it as t instead of x. It's 15t. Now this would do it, because, hold on a second. Would this do it? Means that every minute that goes by, what's happening?
This means that it's increasing by 15 gallons.
Yeah, means that 15 gallons is going into the pool every minute. Okay, so you're really close. So we could just change that. Y of t equals negative 15t means 15 gallons is draining. It's draining 15 gallons every minute. But there's something about that that doesn't seem to make sense. How can there be negative number of gallons in the pool? If t is 1, there's negative 15. If t is 2, there's negative 30. This doesn't, there's something about it that seems right now, that the water's flowing out, but we keep getting some problems. If we translate the pool is draining at the rate of 15 gallons per minute into strict mathematical symbols, it's y prime of t equals, because whenever it says rate of change of something, then it's really talking about the derivative. Draining at a rate, the way that y is changing, its instantaneous rate of change is, and it's going out, so it's negative 15. That's the real equation. This is what we really want right here as our answer. And the solution of this equation is going to be related to the one right above it. But we have to get rid of that problem of negative number of gallons in the pool. All right. So let's go to number 2. How full is the pool after 5 minutes? And then number 3, find the function that models the situation. So, debate both of these. Think about it yourselves, debate it in your group. We'll go over the answers in just a minute. Okay. Group 4. What do you have for number 2? So, any response from group 4?
Oh, hello. Sorry, my mic wasn't plugged in yet. But
Okay.
what I was saying is, my thought process on 2 was that since there has to be an initial amount of water in the pool, it'll be that minus 75.
Ah, how full is the pool after 5 minutes? The initial amount minus 5 times 15. And 5 times 15 is 75. 5 times 15, which equals 75. All right, so that's really good. Whatever the initial amount was, minus 75. And since you're on a roll, group 4, any answer for the next one? Function that models the situation.
I haven't put a lot of thought into the next one,
Okay.
but
You
yeah,
want
I
to
got
guess?
nothing.
Do you want to guess or you want to pass on
Mm, I'll guess that it's a power to the second since with derivatives it's n minus 1. So, or I don't know. I'll pass it.
it? Oh, you're thinking maybe a second power. Okay.
Yeah, something like that.
All right. I like your train of thinking. Let's look. The derivative function is actually to the 0th power, though. Y of t is negative 15. So if we go 1 power higher than that, we would get negative 15t. And then, so we get something like y equals, but we'd have to have an initial amount. Subtract 15t. Because we went 1 degree higher than this one. So that when you take the derivative of this, now when you take the derivative of any constant for the original amount, you get 0. When you take the derivative of minus 15t, you're going to get minus 15. And that's consistent with this. The only thing that we were missing with this statement way earlier was y sub t is negative 15t. It should have been an initial amount. Subtract 15t. Okay. So, we wind up with this situation in number 4. This is the same as this, but we call it an arbitrary constant. And what we had was y prime, let me just move over here, y prime of t equals negative 15. We wanted a function so that when you took its derivative, you got negative 15. That led us to y of t equals negative 15. But when you take the derivative, negative 15t, but when you take the derivative of negative 15t, you're going to get negative 15. But if you also take the derivative of negative 15t plus any constant c, you'll still get negative 15. Because the derivative of a constant is always 0. All right. Then it asks us to graph y equals negative 15 plus c. Well, how can you graph a function when you don't know what the c is? The c could be anything. It's some initial amount. We could still be asked to graph it though. And let's go to drawing it, and anybody have an idea? How do I graph this when I don't know what the C is?
Could the intercept just be as simply as C
C. But where do we put the C?
on the y-axis?
Should I put it as 1 or should I make various ones? Since we don't know what the C is.
Maybe various ones?
Very good. We'll put the C all over the place. In case the C is any one of these things, we're going to make these lines look like... Now they all are going to be going down. And they're all going to be parallel. And actually, it doesn't make much sense, practically speaking, for them to be to the left of the x-axis. That doesn't make any sense. So let's go to the eraser, and let's erase. Part to the left. And another one that doesn't make sense is if you started down here. That doesn't make any sense in this context. And when you run out of water, you'd stop. You wouldn't go to negative amounts of water. So, but what you're going to get is an infinite amount of curves that are all parallel to each other. And so what you get, it's a family of functions. When you do an antiderivative, this is one of the big lessons, antiderivatives in general, you're not going to get a single solution. You're going to get a family of solutions, which is an infinite number of solutions, because there's going to be an arbitrary constant that we don't know what it is. Later, we might be given more information and say, hey, the pool started out with 500 gallons of water in it. Then, out of all that family of functions, we just pick the one that has a y-intercept of 500. And then we get it. But if we are not given, it's called an initial condition. If you're not given the initial condition, you get a family of solutions. And it's very different when you go backwards. When you're going from a function to its derivative, you always get one answer. But when you're going from a derivative to the original function, you're either going to have an initial condition and then you'll get one solution, or if you're missing the initial condition, you'll get an infinite number of solutions, which we call a family of functions. The family of functions don't necessarily have to be straight lines. They could be squiggles. But if they were squiggly curve, if they were something like this, then the other ones would be just like it, but vertical shifts of it. That would be your family of functions. And then we eventually find out the initial condition is one of these, then all the rest goes away. Okay. So, that's the general point. Now, we want to explain this. So number 5, why don't we get a single function as a solution? Let me just pop that question to group 6 right now. Anybody in group 6 want to offer a possible explanation? Why don't we get a single function as a solution?
It's would be because of the constant.
That's right. When you take the derivative of an arbitrary constant, you always get 0. So when you're going backwards and you're saying, all right, I want a function whose derivative is negative 15, you always have to stick on plus an arbitrary constant, plus a c. Because its derivative would have been 0, it wouldn't show up there. But when we go backwards, we have to account for that. All right. So, finally, number 6. Solve the initial value problem. dy dx is negative 15, and y of 0 is equal to 900. Let me give you a minute, and then I'll call on a group. Okay, group 2, do you have an answer for this?
Yes, we have negative 15t plus 900.
Y equals negative 15t plus 900. And so what you did basically is find a function who, when you take its derivative, you get negative 15. And is that true of this function? Yes. And when you substitute 0 in for the t, you'll get 900. Yes. It meets all the conditions. And it's the same problem if the pool originally had 900 gallons of water in it. Then 1 minute later, it's 15 gallons is drained away, etc. All right. Before I go on from this, just give me a little feedback about the clarity of this. Are you all clear with this and ready to go on, or do you need a little more review? Is this good? All right. So let's go to the camera. Let me put my whiteboard back up. All right, we're going to now, we took a problem in context. I like to start with a problem that you can kind of relate to, instead of just start with all these abstract problems. Well, let's go now to some abstract problems, and you can see how that concrete problem applies here. If you have y prime equals x cubed, find y. And then we give everybody 30 seconds. Just think about a function that when I take its derivative, I get x cubed. All right. I would say, well, it's got to be 1 power higher. X to the 4th. Because when you take the derivative, it becomes 1 power lower. But if I just did that, that wouldn't work because I'd get 4x cubed. So I got to get that 4 to cancel out, so I'm going to have to put 1/4 x to the 4th, like here. And if I do this, am I done?
No.
What am I I missing?
Your C.
Very good. Because if I put plus 100, its derivative would still be this. If I put plus 1,000, its derivative would still be this. The derivative of any constant is going to be 0. And so we're going to have to put this, and something new that we have to learn to do. Whenever we take the antiderivative, we're going to have to insert a plus C. Okay. Now, number 2, dy dx is equal to 5x to the 6th. Find y. I'll give you a minute to do that. Alright, so we gotta have a function that when we take its derivative we get this. So I know its power has got to be x to the 7th, because it gets 1 lower when it becomes this. But if it was just that, I would get 7x to the 6th. And what has to happen? I have to get rid of this 7. And I have to have a 5 come in its place. And I would have this. Now this derivative is going to be this, because the 7's will cancel out. And then I, of course, have to remember this plus C over here. Alright, now, starting to get the hang of it. But there's notation. The notation look at it like this. The notation of okay. How we're going to read this is the indefinite integral with respect to x. Now, the indefinite integral with respect to x is the same as the antiderivative. But we're going to get away from the name of antiderivative and we'll be going to this indefinite integral idea. And this indefinite integral is a whole new symbol. Kind of looks like a really elongated S. It's super long on the midsection. And it has to do, we'll eventually see that it's supposed to look kind of like an S, and it's going to have to do with summing up some stuff. We're going to get to that eventually. And this dx is going to get a more interpretation later on, but for right now, we'll just think of it as with respect to x. So it's this, the indefinite integral, notation for indefinite integrals. Integrals is this. And this becomes x to the 4th over 4 plus a constant. Or 1/4 x to the 4th plus a constant. Alright. Now, we're going to be doing lots of these. And so, we don't want to be kind of struggling every time and saying, oh, what's the function whose derivative is this? We want to make up new rules for this. And then, the first one we're going to do is the power rule. For indefinite integration. And you can call this the antiderivative, but we'll be losing that terminology. We'll more commonly call it the indefinite integral of x to the n dx is equal to, all right, now when we did it over here, think of this as the n now. You get 1 power higher than that. So it's just going to be x to the n plus 1. But you want to get rid of that n plus 1 right over here. So when you take the derivative of this right-hand side, it should match this one. And the n plus 1 will come down and get canceled out by the n plus 1 in the denominator, and then you decrease the exponent by 1, so it'll match, plus a constant. That's the power rule for indefinite integration. And then we also want to look immediately at a property. If you have a constant, times, well, we'll just say times any function. The constant gets to come out front. And this rule helps you do a more complex problem incredibly quickly. So all you do is say, the indefinite integral of this one, you bring the 5 out front, so it just stays there, and then this becomes x to the 7th over 7. And then, there you go. So, let me paste this. Any questions or comments? All right. Let me have you practice some. We'll start over with number 1, practice. The indefinite integral, 3u to the negative 2 minus 4u squared plus 1 du. Now, it turns out that we also have this property. The integral of a sum is the sum of the integrals. So it means you get to do them separately. And you get to take the constants out front. When we combine these things together, we wind up being able to do these very quickly and efficiently. So let me give you a minute. See what you get with this. Alright, so I'm going to distribute the integral and make it 3 separate integrals, but I don't have to write it out like that. And then I'm going to pull out the constant out in front. And then this is just the integral of u to the negative 2 du. And then what do I do according to the power rule for integration? I add 1 to the exponent and then put it over whatever that exponent is. And then minus 4, the constant comes out in front, and then this one I add 1 to it, so it becomes u cubed over 3. And then this one, the exponent is 0 plus 1x to the 0, so add 1 and it becomes 1x. X to the 1 over 1 is just x, no, not x, u. Now, when I did this one, I get an arbitrary constant. When I do this one, I get an arbitrary constant. When I do this one, I get an arbitrary constant. So I could write plus C1 plus C2 plus C3 for 3 arbitrary constants that came about. But the nature of arbitrary constants is something that takes a while to get used to. If you add 3 arbitrary constants together, what do you get? An arbitrary constant. So instead of doing those 3, we can just put 1 plus c. You get some unknown number. It could be the initial amount that you started your pool with. And finally we clean up this, and we're going to get minus 3u to the minus 1 minus 4/3 u cubed plus u plus c. That's my antiderivative. Now, when I'm done with my work, it's really easy to check. I just take the derivative. Negative 1 to the negative 3 is positive 3, u to the negative 2. Multiply these, those cancel out. I'm going to get 4u minus 4u squared plus u, and that's it. So the derivative of this always has to match up with this. We're getting a fair ways into this indefinite integral and antiderivative. Okay, let's do another one. All right. Number 2. I'm going to put this up, I'm going to give you a little time, and you can consult in your group on this one, and I'll call on a group in a minute. 5s plus 3 squared ds. Alright. I'll give you a minute, and you can consult. Work on it individually to start with. Okay, anybody need more time? All right. Group 3. How would I start this?
Hold on, we're consulting.
Okay.
I was thinking you could write the 2 out front and have the function of 5s plus 3 as the denominator.
Okay. And how do we take the antiderivative then? What power will be on the S when we're done? The highest power that will be on the S when we're all done.
Wouldn't it be a 2?
For derivatives, we always get 1 power less. So for antiderivatives,
Oh.
we're going to get 1 power more. So the highest power on the S here is squared. So in the end, we're going to get cubed. Okay? Now, if you did this one without trying to FOIL this out though, it's not going to work for us. The only way this one's going to work is like this. And then we're going to get 25s squared. The two middle terms are going to be 15s, 15s. That's going to make 30s. And then plus 9ds. So what we're going to have to wind up doing is simplifying this as much as we can. And then we have one of the properties that allows us to say the integral of a sum is the sum of the integrals. It doesn't turn out to be the integral of a product. Alright. So one of the points that I'm making with this is that there is no product rule. For integration. You can't say it's the integral and then squared or something like this. And this kind of makes sense though, because remember the product rule for derivative was really complicated. So when we reverse the process, it turns out there's just no product rule. So we just got to do this, and then we're going to get 25 and then s cubed. Instead of putting the over 3 here, I'm going to put it over here. 30s squared over 2 plus 9s. And then you get a C1, a C2, and a C3. But the sum of 3 arbitrary constants is an arbitrary constant. That's my final answer. Okay, let me copy this. And then let's do number 3. something, I'm going to wind up doing this. Secant x dx versus the integral of secant squared x dx. Alright, so let's look at these things for a minute. The derivative, what was the derivative of secant x?
That was secant x times tan of x.
Secant x tangent x. Does that help us take the integral? It turns out not. What was the derivative of tangent x?
Secant squared.
Secant squared x. It turns out this is going to help us out over here. Now, why is this going to help us out? When we're trying to find an antiderivative rule, what we do is do something like this, and we take the antiderivative of both sides. So I'm going to do this and stick a dx and this with respect to x. Okay. Now, what's going to happen is the right-hand side is just this. The left-hand side, two things are happening to the tangent x. Its derivative is being taken, and then its antiderivative. It's kind of like taking 5 and then squaring it and then square rooting it. You're doing a function and immediately followed by its inverse function. If you square 5, you make it grow to 25, and then you take the square root of 25 and you're back to 5 again. What happens is, taking a forward function and an inverse function, this and this is antiderivative, this is derivative. They kill each other off. And all you're left with is tangent. Now, when you take the integral of something though, you always have to remember you have to stick this plus c. So let's just turn this around. We get this. What we find out is that something strange is happening. We can find the integral, or the antiderivative of secant squared, but we can't find the antiderivative of secant. How come we can't find the antiderivative of secant? Because it was never the outcome of a derivative. Whatever was the outcome of a derivative can be the input for an antiderivative, and then we have it. This one, we don't know. And eventually we'll figure out a very creative way to get there. But right now, we just say we don't know yet how to do one of those. So this is another really important concept, is that we can reverse things, but we can only get the things as inputs for an antiderivative had to have been outputs from a derivative rule. So I can take the antiderivative of sine and cosine and secant squared, but I can't take the antiderivative of secant because it was never the output of a derivative rule. And what becomes interesting too is, remember when you take the derivative, d dx of sine x, you get cosine x. And if you take the derivative of cosine, you get negative sine. Well, it all works in reverse. The derivative of cosine x, or the antiderivative of cosine x dx, is sine x, because the derivative of this one has to give you this. The antiderivative of sine x dx is not cosine x. Because if you take the derivative of cosine x, it doesn't match this. You'd get negative sine x. So you have to put a negative. Now the derivative of this, you'll get an extra negative to match that. And so the derivative of sine x stayed the same sign, but now when you take the antiderivative of sine x, that's the one that has the negative in it. And so things become a little bit strange because we're going up the chain backwards. All right. Any questions?
So what about for cosecant?
Cosecant is going to have the same problem that secant had. Cosecant squared, remember, that's the output of the derivative of cotangent is negative cosecant squared. So if you just multiply both sides by -1, you can get that. Being off by a constant is not a problem. So cosecant squared, yes, we can get its antiderivative, but we can't get the antiderivative of secant. Okay, and then if you read in the section, it'll give you more details on the antiderivatives of basic trig functions. And they're all listed. It's page 325. And all right, so let's go on to motion problems. And the motion problems we had one in the practice quiz today. And we were given a height function, and then we had to find the velocity and the acceleration. Now we're going to get problems that go in the other direction. If all we're given is the acceleration, but we'd also need to be given some initial conditions. V sub 0 is 12 and S sub 0 is 35. Okay, so here's something that all we know about is its acceleration is negative 9.8. That tells us it was at the surface of the Earth. Okay? If you're on the moon, it's significantly less acceleration due to gravity. Its initial velocity was 12, probably meters per second, since this was 9.8. Its initial height was 35. We can go backwards from this. When they say a of t is negative 9.8, they're really telling us s prime prime is negative 9.8. Because the acceleration is a second derivative of the position function. Now, we're going to take the take the indefinite integral of both sides. Now, if we do that, we're going to put this dt All right, so when you take this integral, the antiderivative of a second derivative, you'll be left with the first derivative. Take the antiderivative of this. Well, what's a function who, when I take its derivative, I get the constant 9.8. It must have been negative 9.8 t, because its derivative would be that. Or you could just use the power rule. This was t to the 0, so you go 1 degree higher and then divided by 1, and then plus an arbitrary constant. Alright, so we now know this, but this is really the velocity function. So the velocity function was this. But we don't know, just like we didn't know what the initial amount in the pool was, we don't know what the initial velocity was. That's why we had to put it plus c. But this initial condition will now tell us that. Plug in v sub 0 is equal to 12. And then 0 goes in for t. V sub 0 equals negative 9.8, 0 plus c. But v0 is 12. And that becomes 0 plus c, which is c. Thus c is 12. And we can go back now and write vt as a single solution instead of an infinite family of solutions. So we went backwards and recovered the velocity. Now, let's go backwards one more time. Take the indefinite integral of both sides of the velocity. And if I do, I get this. Like this. Now, I'm going to think of the vt not as vt though. It's really s prime of t. When I take the antiderivative of s prime, I'm going to get s. When I take the antiderivative of this right-hand side, I'm going to get negative 9.8 t squared over 2, power rule with the t, plus 12t, plus an arbitrary constant once again. But I know what this arbitrary constant, how it can be determined. We know this right here. Plug in S of 0 equals 35. This equation becomes S of 0. And negative 9.8 divided by 2 is negative 4.9 t squared plus 12t plus c. But these t's are now zeros. So this tells me that S of 0, but S of 0 is 35. Everything except C zeroes out, so C is 35. Thus, S of t is this equation, negative 4.9 t squared plus 12t plus 35. And we've got it. It said find S of t. It had to have original height of 35, original velocity of 12, and we just worked up the chain with antiderivatives to get all this. Notice how we needed two initial conditions because we had to take the indefinite integral or antiderivative twice to go from S prime prime all the way back to S. And let me copy that. And we are out of time. Any questions? The homework is this section 4.9. I had on the schedule to do 4.9 and 5.1, but we didn't get to 5.1, so it's just 4.9. 5.1 is a very quick one. I'll be getting to that tomorrow along with doing other stuff as well. Okay, if there's no questions, we'll stop here. I'll see you all tomorrow. And I'll stop the video.